Okay, so I'm going to talk about the dynamics of GPU execution. As I've said before, a topic that kind of went with me throughout my entire career. And as I showed you before, I have been here 10 years ago. And back then, I was also working with the GPU. So what I will do today is I will give you a short introduction to GPU computing, I would say. If you don't know anything about it yet, you will get to know a little bit. If you know everything about it, the first few minutes will be a little bit boring. And then I will show you what we did on top of that, what interesting applications we have found, and what you can do in this direction. Maybe pick up some research for yourself. Okay, so when we talk about the GPU, we have to go back to the 1980s when the first graphics processor came to be, and all we started with was simply having a frame buffer, which means you could simply show something on a screen. And then slowly we added, or we humans added additional stages. So what you could then do is do some fragment processing, and we even had a rasterizer, so you could figure out which pixels are covered by a triangle. Of course, that's pretty boring, so we ended up adding additional stages, and then suddenly in 1999, you could also do vertex processing, which means you could finally do animations potentially on a GPU, and you could do the projection on the GPU. It was back then not called GPU yet, but we're going to get there soon. And finally, in 2001, we got some programmable shaders, and this means you could finally actually program the GPU yourself to do vertex shading in completely free manner. You could do fragment shading in completely free manner. You also know this. And then we started to add more and more stages. So then the geometry shader came, and we also started to have compute mode execution, meaning CUDA. And you also know that we added things like tessellation, and now we're already in the year 2009. And you know that today the graphics pipeline mostly still looks the same. So we have got a couple of fixed function units in there, and we have got a couple of programmable stages, but that's about it. Well, today, actually, we can say that some things are changing, and some things actually have changed quite recently. We have some new technology now, which is called mesh shaders. So somehow we have taken the back part of the pipeline, we kept it the same, and we changed the entire front part. So now there is a thing called a task shader, there is a mesh shader, and this means you can somehow more dynamically do anything here and then just rasterize it. There's also things like ray tracing coming up, where we now have got shaders to do ray tracing. We have heard it in the talks today, I think, that some of you have already tried those things. So the landscape is changing again. And the question is, where does the GPU go from here? And how is the GPU going to look like tomorrow? And this is something that we are interested in. And one option might be that we are just mostly going to be doing things in compute. Because we know that this is like the most flexible thing. Before, we always had these stages lined up in a fixed manner. And now we see things going in a more general manner again, where we have these mesh shaders. So potentially, we might just go in the direction of pure compute. Probably it's not just going to be pure compute, but we are going to go in the direction of being more flexible again. So that's just about graphics. But we also know that the GPU is used for more things by now. Why is this interesting? Because actually GPUs have loads of performance by now. This is mostly driven by the need for more flexibility. Applications are getting more and more diverse. And we also know by now that the simple pinhole camera is simply not enough. If you think about VR, AR, we are doing loads of screen space effects and so on and so forth. So actually the projection itself is probably the simplest and the smallest thing that we are doing. Okay, so the question is, where do we go from here? How will the GPU change? Are we going to get more and more application-specific extensions, like we are seeing now with ray tracing, that we are putting some ray tracing cores, we are putting some cores for this, some cores for this, like for deep learning, for example, and then we have to somehow string them together. Are we going to get more and more programmable stages? Is it going to be more different pipelines? Is all of these things going to be fused together? We don't know. We have got some ideas, and maybe you will end up with some ideas later at the end of this talk too. And also one thing, if you take a look at, we are still really climbing in terms of performance when we look over the years, when we take a look at the GPUs. And this is why GPUs are not only used for graphics. As you know by now, CUDA is pretty common, and compute mode is really important. And if we take a look at supercomputing, this is a list of the top 10 supercomputers. We can see that the first 2 and 3 of the top 5 are actually powered by GPUs, and 5 of the top 10 are powered by GPUs. Which means GPU computing in general is getting more and more important, also in the direction of supercomputing. And if we take a look at the accelerators used in supercomputers, then we can see that the GPUs are climbing too, and we now are already at 120 of the top 500. And this is going to get more and more important because GPUs are really power efficient when we take the ratio between compute and power. Okay, so much about that, sorry. What am I going to talk about today still? I'm going to talk a little bit about the GPU architecture. Then I'm going to go down the road of what you can actually do differently when you execute things on a GPU if you have got dynamic problems. I will show you some example applications, mostly from computer graphics, so that you feel comfortable. Then we take a look at a completely software-based rendering pipeline, and we then might go and see a little bit of linear algebra and maybe dynamic graphs still. Alrighty. Sorry. So before I want to tell you about how a GPU works, just a quick raise of hands. Who has actually worked with CUDA or any other programming language for a GPU, like OpenCL or whatever? Okay, so quite a lot. Who has never done anything on the GPU, not even rendering? Okay, 1, 2, cool. GPU architecture. So the GPU consists of a set of single instruction, multiple data units. Who knows what SIMD is? Do I have to explain it? Who does not know what SIMD is? Okay, you a liar. Anyway, okay, a couple. So the idea of SIMD is that you have a single instruction that is executed on multiple data words. And this is a way to make things more efficient, because then you only have got one instruction and you do the same thing multiple times. This is what the GPU is mostly about. But actually, it's not just one big SIMD thing, the GPU. You have got multiple SIMD units, and these SIMD units are strung together into multiprocessors, and each multiprocessor has a couple of SIMD units. So you can do a couple of different instructions on some groups of threads. And them being strung together into multiprocessors, you then also have some efficient memory on the multiprocessors. Okay, and there is some global memory, which is a little bit off the GPU, so it takes a little bit longer to access it. And this memory is usually quite huge, and you have got quite a high bandwidth there still. Okay, so much about the principal idea of a GPU. And if we write in code for the GPU, usually write things in terms of kernels. So what you do is you write code for individual threads, but these threads are all strung together into warps. A warp is a group of threads that's executed on one SIMD unit, and then you are stringing multiple of those together into a block, and the block is then executed on one multiprocessor. That's the overall idea. And then you string multiple of these blocks together into a grid, and this gives you a kernel. And so you're writing one set of code that is executed by tens of thousands of threads. That's the overall idea. And all of these threads usually start executing the same code. So you can imagine that this is pretty well suited if you, for example, want to do image processing, because you have got many, many pixels, and you, for example, want to do the same instruction on all of those pixels, like, for example, convert this to grayscale, blur it, whatever. So this is really straightforward. This works trivially, and I guess everyone who has started with CUDA or anything alike has done something like this, because it's really straightforward. So the problem is, let's take a look at something which is a little bit more complicated, like the rendering pipeline. So if we're doing rendering, we know that the GPU can do rendering, at least most of us do. Then you have a problem set like this, where you start out with some input data, you have got lots of vertex shaders that you want to run, then this leads to a different number of triangles, then you want to rasterize those triangles, and depending on the triangle size, you have got way differently sized numbers of pixels that are being covered, so you need way different number of fragment shader invocations, and then all of this must be blended back together in the frame buffer. The question is, how could we do that with this kernel-based model that I just told you before? Any ideas? Very good. If you had a good idea, this would not be good, because then all of my research might be void. So the thing is, there's just simply no good way to do this, because you have got all of these different kinds of things that you want to do, and you cannot just pack this into one kernel, because the parallelism changes, the different things that you want to execute change, so this is really not well suited for this kernel-based execution model. But the thing is, we know that the GPU can actually run this pipeline efficiently. So the question is, what can we do about this? And a lot of people had the issue that they wanted to do something more dynamic on the GPU, which is pretty obvious, because there's this huge amount of computing power that you have with the GPU, and you somehow want to use it. So one of the early approaches, also in 2009, when I had no idea about all of this yet, is the persistent threads model. So the idea here is that you start worker blocks, and these worker blocks are not dedicated to just run the code for one input data, like one pixel, but what they are doing is they are running in a loop. So they're actually running in an endless loop, and you provide work to them with a work queue. And this means that they can actually draw in work and start executing this work, and when they are done, they are just gonna draw in more work. And in this way, you have got more control over the execution. You can do load balancing yourself, and so this gives you some kind of flexibility, makes the GPU more dynamic. The problem is that you only have got one task type, because all of them just execute the same code. So then, a couple of years later, we came about and we said, okay, we want to do more dynamic things on the GPU. What can we do? And the idea is, okay, instead of just having one type of task, we want to be able to run different kinds of tasks, right? As I said before, for example, vertex shading, fragment shading, and so on and so forth. So we figured, okay, we're just going to extend that. We have got different tasks. And what we also wanted to have is dynamic work generation, which means while you execute something, you want to be able to say, oh, there is something new that I want to execute. I want to launch one thread for this. Of course, this usually doesn't work efficiently on the GPU, because there's lots of overhead with starting new things, and you can only launch large kernels, something that we heard also today in the last talk. So we figured we build a work queue, we allow threads to enter things in this work queue, and we take out other tasks from this work queue. That's actually not so straightforward, because suddenly you have tens of thousands of threads that want to do something with this work queue at the same time, and all of the algorithms that you have on the CPU don't work well on the GPU anymore. But I'm not going to go into detail here anymore. There's also a problem with the SIMD execution, because you have got threads that run different code, which means you work against the SIMD model, which is called thread divergence, so you don't get a too great performance. So at the same time, NVIDIA essentially figured, we are going to solve the problem for everyone. We are going to come up with dynamic parallelism. And as we have heard today too, with dynamic parallelism, you can launch kernels again from the GPU. So you can launch a block or a kernel, and then this block can launch new blocks, these blocks can launch blocks, and these blocks can launch new blocks, and so on and so forth. There's some limits to this, but in the end, you can have some dynamic work generation on the GPU. The problem with this is that you don't have any fine-grained work generation, which means if you want to start small blocks, individual threads, or many, many blocks, as we've also heard today, then your performance will suffer. And there's more things, like you cannot use the local memory on the multiprocessors, as we have seen before, which is quite efficient to communicate with new threads that you start. So in this way, we figured, okay, we have to do more because our first attempt was not working too well. The things NVIDIA provide don't work too well either. So we came up with what we call Whipple tree. So for Whipple tree, we decided that we should go back to the drawing board. We knew that the concept of threads, warps, and blocks totally makes sense because this is how the GPU works, right? We know that there are these SIMD units, so we want to provide multiple threads with the same work to run on the SIMD units, so this means we need warps. We know that we have got the multiprocessors where you want to have entire blocks that can cooperatively work. So the only problem that we essentially saw was this rigid grid thing, because if you have got, or if you can only launch these really large kernels of identical blocks, then things just are too rigid. And so our idea is that if you write an algorithm for the GPU, you should not be stuck with just launching a big kernel after another big kernel, but you rather want to start by maybe one block, a couple of warps, a couple of threads, and then as these threads or warps just progress through the algorithm, they figure out, oh, there is something new to do. I want to start another warp. I want to start another block. And then you just hand it over to a scheduler, and the scheduler finds the best way to execute it on the GPU efficiently. And you can actually implement this model in software again quite efficiently. So the idea is that we went back to having these worker blocks, and now we are using multiple queues to store tasks and collect tasks. And the worker blocks again run in a queue, in a loop, and they draw work from these work queues that we have. And one of the key ideas is that you always draw identical work into one block. In this way, you don't have the problem of thread divergence anymore. You can also dynamically, again, generate work for these work queues. As we said, different tasks, minimal divergence, and dynamic work generation. There's one really important thing that you can now do is you can do load balancing. You can dynamically decide from which queue you want to draw work. You can also maybe have multiple queues with different priorities. You can come up with completely arbitrary execution orders. And this gives you loads of flexibility to tackle the problems that you have most efficiently. Okay, and you can even do one more thing. You can also build local queues, which means your worker blocks can now use the memory on the multiprocessors and store data there temporarily or tasks there temporarily, and then you would simply prioritize taking the work from these local queues, and if you don't have anything locally, you just grab it globally. And in this way, you actually end up with a programming model and execution model that works really efficiently, and you can tackle loads of problems that usually would not fit the GPU well. So after all of this theory, so to say, I will show you a few examples that we have done so far before we dive into some other problem domains. So what you can see in here is some real-time Rasterization rendering. Who knows what Rasterization is? Something to be expected. So Rasterization stands for render everything you ever saw. A technique that has been used by Pixar until recently for rendering subdivision surfaces, for example. And one of the problems of this rendering pipeline is that you have got this loop in here, where you split geometry finer and finer before you essentially figure out which pixels are covered by this geometry. So implementing this pipeline was pretty difficult previously to just run on the GPU efficiently. And what we did is we figured out what are the best ways of parallelizing these individual stages in terms of how can we execute it most efficiently. So we have got, for example, this first stage would use 16 threads, the next stage 4 threads, then this stage 256, and the final shading stage only a single thread. So you can see different kinds of parallel, also different requirements in terms of registers and shared memory. So if we implement this pipeline in a traditional way, where we, for example, only use a single thread for every single step that we want to take, then we get a performance like this in here. Just ignore the different techniques, they are all similar, and you can see that this is the execution time. So if we rendered a single frame with 1,000 milliseconds, that would not be overall too great if we are targeting real time. So if we now use our model where we have the ability to use this setup of having individual warps, individual blocks, or individual threads, we suddenly get a huge performance boost. This is a log scale, so if we show it in linear scale, you can clearly see that this is way faster than what you can see in here. And in the end, it's more or less just the same instructions that are being executed, it's just way more efficiently scheduled, way more efficiently packed together. And this is all what efficient GPU execution is about. Okay, it's not just about performance, it's also about doing things that you could not do before. So here's an example which is called IRradiance Caching for Monte Carlo volume rendering. What we're doing here is we are raycasting a data set, and we want to, on the fly, build an IRradiance cache. And what we're doing is, when you cast array and you hit the point, you figure out, is there a IRradiance cache sample? If it is there, you use it. If it's none, you want to schedule the creation of one. But at the same time, you always want to ensure that you have got interactive frame rates and you show things to the user immediately. So our target is that we always want to spend at least 80% of the GPU's performance on casting our primary rays, and a maximum of 20% for cache creation. So in the beginning, when the cache is empty, we can set up the system in such a way that it automatically schedules cache creation only for 20% of the time and 80% for raycasting. And then as the cache grows fuller and fuller, it automatically can reduce the time spent on cache creation. And if the cache is completely full, we spend hardly any time on cache creation. As the camera moves, for example, in the middle here, you will see this small tilt where we suddenly again need more time for cache creation. So all of these three processes, also cache update, are running concurrently on the GPU, and the scheduler takes care of fulfilling our requirements. And all of this is just possible because in the background we have got these work queues, and then decide what's currently most important, how much time have we already spent on something, what should we do. Okay, another thing that we built with the system is some procedural generation. Actually, it's a shape grammar mostly, and I'm just going to show you the video. What we've done here is we tried to combine procedural generation with rendering, and we are building geometry just on the fly as you're moving through a scene, and we're trying to keep geometry from the previous frames, and we also want to adjust the level of detail of everything that we build according to the current view. And all of this is running on the GPU, nothing is being done on the CPU, and everything is dynamically generated. And as you can see with this fly-through, as soon as we are gonna switch on the wireframe, you can see how buildings are regenerated, how roof tiles are added. And in the background, there's of course a complex memory management going on, scheduling of all of this, determining how much time we have, what we should build, what we should not build, what we can still keep from the last frame. This is already, I think, 6 years old by now, and still back then we achieved pretty decent speed. You can see some popping of level of detail because we did not set it up completely perfectly. But with this, you can fly over completely random cities with nearly supersonic speed, and this still works completely efficiently, unless you're just gonna run into a skyscraper. Okay, so much to procedural geometry. Talking about prioritization, like figuring out how much time you have, you can also, of course, figure out where you want to use your compute performance most efficiently. So some classical thing is that you, for example, do some path tracing, and the idea is, if you, for example, know where the image quality is not too great yet, then you can, of course, direct compute power to these areas. And in this project, we did that completely on the GPU again, everything dynamic. So we figure out where we expect the most gain when we add more samples, completely dynamically, and just direct the execution to these areas. And this, of course, works then for all kinds of effects, whereas we have to say that path tracing is not too complicated because a frame is not done so quickly that the scheduling needs to be really imminent, but we still can do that completely autonomously on a GPU and just get better image quality, as you can see here on the lower side, than uniform sampling. The same idea we applied again to Rasterization rendering, and what we want to do here is we want to guarantee certain frame rates. So on the left side, you see traditional Rasterization rendering where we always subdivide until we hit a certain smallness of our subdivision. And on the right side, you see a prioritized version, which is actually going towards foveated rendering, where the user would be looking where the cursor is. And in color-coded, you can see how much processing power we direct to which regions. And as we prioritize the execution, we can also say, now we are close to the end of our target frame rate, we cannot do anything more. And then we can simply stop the subdivision and say, okay, we are just gonna shade our pixels now. And in this way, we can guarantee frame rates mostly independent of how many objects we have in the scene. So on the left side, you will see that the rendering becomes slower and slower, whereas on the right side, we still have our perfect frame rate target. And yeah, and here you can see again the focus region where somebody would be looking and where we spend a lot of time. So this is something that you can also, for example, or might also see in the future for VR, because we are now at a point again where we don't have enough processing power to render everything in high quality. Okay, so much about prioritization. Now I'm quickly gonna go on to a next example, which is some work that we published last year at SIGGRAPH. It's called Cure Software Graphics Pipelines for a GPU. And what we wanted to do here is figure out how can the graphics pipeline of the future look like, and how fast is actually a pure graphics pipeline if you implement it efficiently just using compute. So we are running usual graphics on the graphics chip, on the GPU, but we are not using the hardware, only doing everything in software. So no rasterizer, no tessellation, no vertex shader, just simple CUDA, essentially. So for this experiment, we essentially just took the standard graphics pipeline, you know how it looks like, and then we figured, okay, how does the usual pipeline look like? So we are not doing tessellation or anything here to keep it simple. And if you look at it, traditionally, you split the pipeline into two stages. So you have got some geometry processing at first and some rasterization later on. And this is the typically sort middle setup. And on the first part, you actually work in object space, right? So you do vertex shading, you work on triangles. And on the right side, you're working in screen space. So you can see that there's two completely different ways of parallelizing this. Because on the left side, you probably have got fewer things. On the right side, you might generate loads of fragments, maybe only a few fragments, maybe no fragments at all. And when we take a look at geometry processing, we have got vertex level parallelism and primitive level parallelism. So this means scheduling this efficiently and running it efficiently might not be too trivial. And also there's things like primitive order, where you have to make sure that fragments that leave the pipeline do this in the same order as triangles enter the pipeline here. Okay, so people have tried to implement rendering pipelines in software before, because that has always been interesting for graphics researchers. And if you do that, you would usually do it with multiple kernels. And the idea is you would at first run the first stage with a kernel. For example, you would do your vertex shading, and then you would write all of the results out to global GPU memory, as we have seen before on the side. Then you would run the next stage for all of the triangles, and as you're done with all of the triangles, you would do the next stage, you would do the rasterizer, then you would do the shading, and so on and so forth. And every single stage would go out to global memory. And the problem with this is that you, of course, generate loads and loads and loads of memory. Because if you think about it, we are now rendering scenes with millions of triangles. We don't want to know how many fragments get shaded. And if we store all of the temporary data always out to global memory, this uses loads of memory and would potentially be really slow. So what you have to do is you have to build a streaming pipeline, which means you start with the first stage, you run the first stage with a few instances, and then as soon as the first stage is done for some output data, you immediately start with the next stage. And the other processes, they're done with the first stage, they can start with the second stage. And as something is done with the second stage, you immediately go to the first stage somewhere else. And in this way, you essentially split your execution in the most efficient manner, and you can in this way keep memory requirements low, you can run more efficiently, and you also bound the overall memory. And this is also how the hardware rendering pipeline actually does it. So the question is there a way to do this efficiently in software? And we were looking into this and found the following way of actually running this. So we are doing a global sort middle, which means somewhere we have to go out to global memory. We somewhere have to do big rescheduling to get this difference between object space and image space parallelism. So in between, we also need some kind of rescheduling because we know we're working on vertices, and here we're working on triangles, and in between here, there's also a couple of stages where we need to adjust our parallelism somehow. And we call this locally sort everywhere else. And this means there is going to be some kind of queuing or rescheduling happening there too. So you already know most of the concepts that we use to implement this kind of efficiently. We again have some worker blocks, and now the idea is the worker block can either run geometry processing or it can run rasterization. And we have got work queues again, and here we have got work queues for every single worker block essentially. And these are essentially rasterizer queues. The idea is we have got some input primitives. These input primitives need to end up somewhere in the frame buffer at some point. And we start by executing geometry processing with a couple of the workers. They take the input primitives, and as they are done with them, they are putting the triangles into the rasterizer queues. This is our global sort middle architecture. And as soon as there is work in the rasterizer queues, the rasterizers start working, they take out the work from the rasterizer queues, and at the same time, some other blocks can again run geometry processing. So this is this typical load balancing that you would expect. And the rasterizers then output data to the frame buffer. So if you build this architecture like this, you end up with a pipeline which looks somehow like this if you want to draw it. You have got the vertex processing, which can happen in parallel, some rescheduling in between locally using the on-chip efficient memory. Then you have primitive processing. Then you go to the rasterizer queues. The rasterizers are usually done in a hierarchical manner, so there you need some rescheduling again. And then the fragment processing actually happens somehow multiple times to consider blending. But I'm not going to go into too much detail. So if you implement all of this, the question is, how fast can you actually be? So what can we actually do in terms of compute? And that's probably one of the few performance numbers I'm showing you for this project. So the idea here is that if you do quite some simple shading, you're more than 10 times slower than doing the hardware pipeline. So that's not too great, but it's actually not so bad as one would expect. If you then do actually some computations, like some vertex-heavy shading or some fragment-heavy shading, then you get down to 5x or maybe even only 2 to 3x. So that's already a pretty decent performance because all you do is just do everything in software, and we know that hardware can be very efficient. And if you take a closer look what's actually dominating performance, then it's pretty interesting. One thing is primitive order, the orange parts here, which means making sure that the fragments end up in the right order is actually pretty costly because we need to do sorting in between. And another thing is blending. So blending is this part here, and this is usually done by the hardware in terms of the ROPs. So everything else is actually kind of efficient. So we might not even need that much hardware. And what does a software pipeline give you? A software pipeline gives you loads of flexibility. So you can build arbitrary pipelines. You could, for example, do some foveated rendering, checkerboard rendering combination, where you switch things dynamically, change the rasterizer internally to be way more efficient. You can do any kind of programmable blending. You can, for example, figure out that your underlying geometry for your height field is not ideal, and you can dynamically adjust the geometry completely arbitrarily. Loads of things. I'm not going to go into more detail here, but you can imagine that as everything is in compute, you have got the entire field free to do whatever you want with it. And this is why compute might become really interesting in the future. Okay, I'm quickly going to show you something for 5 more minutes, and then we might be able to keep the overtime low. Sparse linear algebra. Something not entirely related to graphics, but something I should go into because I think it's really interesting. So who knows what a sparse matrix is? Very good. The idea is if you have got a matrix with loads of zero entries, you don't want to store all of the zero entries. So everything which is white here is just zeros, and we don't want to store that. This can also be used to represent graphs and so on and so forth for FEM simulations, linear programming, everywhere in scientific computing, essentially. So why are these matrices interesting? First of all, it's interesting from a low-level GPU execution perspective because you've got really simple operations. This is a simple matrix vector multiplication, and this is really straightforward, you would say. If you ever want to do that really efficiently on the GPU, you will immediately see that that's not so trivial because there are loads of small things that impact performance quite a lot, and a lot of companies, including NVIDIA, have spent loads of time optimizing this. We looked into this and we figured, what if we do things a little bit more dynamically? What if we adjust the algorithm locally? And quite interestingly, here orange, this is our implementation, we can actually gain quite some performance in comparison to the other implementations. So just by doing things adaptively, we can still boost the performance of really highly optimized algorithms on the GPU. We did the same thing for matrix-matrix multiplication, a little bit more complicated, our performance here in red in comparison to the others. And also here, we are beating them quite significantly. Okay, so I'm not going to tell you how we did all of this optimization and all of the details because that might not be so interesting for you, but I want to come back to graphics. So, having a sparse matrix, what does that have to do with graphics? And interestingly, you can also represent meshes as sparse matrices. Because here what you can see is a simple phase table, something you might have seen before, where we just enumerate the vertices for the different phases. And we can immediately turn this into a sparse matrix. And we can even encode that more efficiently, so we also end up with about the same memory requirements of a phase table in a really efficient manner. So, what does that give us? Well, we can now go ahead and say we have got a mesh matrix which describes our mesh, and now we can run operations on top of that. For this, we're using what we call action maps. These are kind of the hands and arms of our matrix operations. And quite interestingly, you can use previous standard matrix operations like matrix vector multiplication, matrix-matrix multiplication, and use that for some kind of graphics output. So if we just tune these operations a tiny bit by just adding a tiny bit the operations, we can get really interesting graphics topics covered by this. So this is quite simple. For example, here we're just computing the triangle normal with a simple matrix vector multiplication with a tiny change down there. We're just swapping out some numbers during the execution. So why is that interesting? Well, if we have got really efficient matrix implementations on a GPU, we can now take all of our mesh processing, turn it into linear algebra, and then put it on the GPU. And by that, get really good and impressive performance. So here's just one video that we published last year at SIGGRAPH Asia, which just uses this kind of sparse linear algebra formulation and really efficient implementation. So what we're doing here is we are growing cells on top of surfaces, and we want to use that for natural tessellations. So when we take a look here, what we are doing is we are essentially generating, I'm not sure, Voronoi-like cells on top of surfaces. Just going to jump forward a tiny bit. Here you can see the cells probably growing one more time. I want to jump a little bit further. Yeah. So here you can then already see that we are, from these initial seed points here, growing cells, and they then end up being Voronoi-like. And what does that all have to do, or why is that interesting? The thing is, we can now run Lloyd-like iterations where we simply move the seed locations to the center of the cells as they grow. And then we get a really nice distribution of points on surfaces. There are multiple applications that we can use that for. One of them, for example, is generating a dual mesh from an original mesh. So for example, if you scan a mesh, you have got a really, scan an object, you have got a really fine mesh, and now you want to approximate this mesh with a low resolution mesh, something which is as close as possible to this object. And this is what you can see here on the left side. We just run these iterations, and then we're getting a really good approximation. And we can do this for really big data sets, and we can run this really efficiently due to all of our formulations that we have in the background and the really efficient implementations. Okay, to keep it kind of on time, I'm just gonna conclude here. I'm not gonna go more into dynamic graphs or anything like this. All this would all be interesting. So the three takeaway messages. First of all, GPU performance is still growing, and it's going to be really important for the future, also in terms of supercomputing. Dynamic algorithms are usually difficult to execute on the GPU, but if you use a task-based programming model like we have come up with, then you can actually broaden the horizon of what you can do on a GPU quite a lot, and you can then use all of this performance really efficiently. You just have to start thinking slightly different, and then you can bring a lot of different problems to a GPU efficiently. And we have been looking quite a lot into dynamic execution. One of them is how will future rendering pipelines look like, how much flexibility can you have there. All of this dynamic execution gives you lots of flexibility, and it can even give you higher performance. So even standard things like this matrix algebra that a lot of people have been looking into, you can still get more performance there, which is of course very important for everyone. Okay, really quickly, that's my team essentially, people I have been working with, and that's it. Thank you very much for your attention.